My name is Nick Visconti. I'm an environmental studies major here at UVM, and I'm a sophomore.
I'm Maggie Williams. I'm a junior and I'm studying environmental science.
Hi, my name's Ellen Thorne. I'm a junior environmental science major with an ecological design concentration.
For our project this semester, we worked with water and nutrient runoff data from the green roof on the Aiken building from May 2014 to January 2015. So let's go see what's on the roof. So here we are on the Aiken green roof. There are 8 different watersheds of varying size and 4 different treatments. Watersheds 1 and 6 are controls, 2 and 4 have alternate plants and standard soil, 3 and 7 have standard plants and standard soil, and 5 and 8 have standard plants and biochar added to the soil. Before we got into all the complicated data, we spoke with someone who could help us get a better understanding of green roofs and the role they play in the bigger picture.
I'm Stephanie Hurley, and I am an assistant professor in the Plant and Soil Science department. I teach classes in landscape design fundamentals and ecological landscape design.
Why should we care about green roofs and other pervious surfaces anyways?
So humans, as we've become more urban in society writ large, and in particular in older cities, have basically laid our mark on the land in the form of pavement, rooftops, impervious surfaces in general. Roads can occupy 30% of a typical city, and you think of roads as public spaces, that's a lot of our public space that we're just dedicating to cars typically, and that mode of transportation. So impervious surfaces writ large wreak havoc on watershed functions. If you look at views from the sky of green roof landscapes spread over lots of buildings, or even photo simulations of what it would look like, you can see what percentage of impervious area would be dramatically reduced in terms of its yield of stormwater during rainstorms.
Now let's take a look at the data from the Aiken green roof. Each watershed had a corresponding tipping bucket to capture and measure the runoff. Each bucket was calibrated in 2014 to determine how much water it can hold in liters. Every 5 minutes, the number of tips per watershed was recorded. The tips were then multiplied by liters to determine their runoff for every 5-minute sample. That means that 288 samples were taken every day for each watershed.
In order to make the data more manageable for comparison, we broke up the data from May of 2014 through January of 2015 into 9 28-day time periods.
Because each watershed is a different size, we divided the total runoff in liters for each watershed in each time period over that watershed's area in meters squared. So we ended up with runoff values in liters per meter squared.
We statistically analyzed this data in the program JUMP. We analyzed if there was a statistical difference in the volume of water discharged between repetitions, time periods, and treatments. We were also curious if there were any significant interactions between repetition and treatment, repetition and time and treatment. We found statistical differences between repetition, treatment, time period, repetition and treatment and time period. We are also pleased to see a very scattered and random residual plot of the data. We ran a Tukey HSD test to determine how the volume data in each treatment was different from one another.
The graph here shows treatment on the x-axis and the least squared means of runoff in liters per meter squared on the y-axis. Each bar represents a different treatment. Different letters above the bar indicate that those treatments were significantly different from one another.
As you can see, the control was significantly different from all the vegetative treatments. The difference between the standard soil alternative plant treatment and the biochar enhanced soil and standard plant treatment was not significant. However, the standard plant and standard soil treatment discharged significantly less water than the previous 2 treatments. This shows that the best treatment in terms of volume discharge is the standard plant standard soil. But overall, any type of vegetative treatment is better than a traditional roof.
The graph here shows time period on the x-axis and runoff in liters per meter squared on the y-axis. Each line represents a different treatment type.
We were surprised at the significant difference between treatments and time periods. As you can see in the graph, the only time period that is out of the ordinary is time period 9, which covers the end of December and the beginning of January. The biochar enhanced soil with standard plants, also the red line, and the standard soil alternative plants treatment, known as the blue line, both discharged more water than the control in time period 9. Although we cannot be sure, we believe that this unusual spike in discharge is due to the frozen, saturated soils thawing out and releasing a large amount of water.
One of our initial goals was the oversight and documentation of UVM's first edible garden. Although the plans and budgeting for this project were approved due to a mandatory stormwater survey, the start date was pushed into the summer. So we started to develop a comprehensive maintenance plan that will allow for the proper care of the garden on a seasonal and temporal scale. The edible garden will consist of berries including lingonberry, serviceberry, chokeberry, strawberry, and blueberry. Winter and spring cleanup, pruning, mulching, and fertilizing are just a few things that had to be taken into account when dealing with constructing a plan to care for the Aiken Center's future renovations.
This project was a huge undertaking in terms of managing and organizing the data. We had hoped to analyze the nutrient data for each 28-day time period from May 2014 to January of 2015, but due to a few roadblocks, we are unable to do this. After lots of trial and error, we have completed a spreadsheet where we've organized the daily volume of water discharged, the concentration of each nutrient, and the flux, which is the volume discharged times the nutrient concentration, for each 20-day time period. We have broken down the data for each watershed so that the data can be easily compiled when it's time to analyze it.
Through this project, we learned how to manage large amounts of data, even if it was through lots of trial and error. And we enjoyed working on it, and we're excited for future interns to finish and explore what we worked on this semester.
We'd like to give a special thanks to our advisors, Gary Hawley and Carl Waite, for their patience and guidance, and to Stephanie Hurley for sharing her expertise with us.